To calculate the elasticity of demand for an item at a specific price, we use an elasticity function or an elasticity formula that you see here. So we say that the elasticity function depends on price, and that's equal to negative p, or of course p is the price, multiplied by the ratio of d primed of p divided by d of p. Now notice this ratio here, d primed of p divided by d of p, is a derivative divided by a function, and so by definition it's a growth rate. So what we have here in this fraction right here is the growth rate of demand. So this is measuring what we call the growth rate of demand. So what we do in order to find the elasticity value at a point or at a price is we take the growth rate of demand and we multiply it by the negative of the price. Another way to write this is to put everything as one fraction. So keep in mind that negative p out in the front there is really negative p over 1. So when we multiply through the fractions, we end up with negative p times the derivative of demand, all divided by the original function d. Now you might be wondering what that negative sign does for us. What the negative sign does for us is essentially assures us that the elasticity value that we get out ends up being a positive value. So it basically plays the role of some of the absolute value symbols that we saw in some previous examples, and so that's all it's doing here. So keep in mind that negative sign, you'll need that to make sure that your elasticity value comes out correctly. So the version of the formula that we're going to use is here in this red box on the right, where we basically have one fraction, and that's a little easier to compute. So let's go ahead and take a look at an example of computing the elasticity of demand at a specific point using calculus. So in this situation, we're looking for the elasticity at a specific price point of $7 if we're given a demand function d of p is equal to negative 8p plus 104. So the first thing we want to do here is actually build the elasticity function. Now the elasticity function depends on the price. In particular, it depends on the price that we currently have this item set at. And we saw from the previous slide that this is simply given by this equation. So negative p times the derivative of demand, all of that divided by the demand function. So when we fill in what we know, we have the negative p out front. That's just sort of sitting there as part of our equation. And the derivative of demand, of course, comes from the demand function. So if we go back up and look at the demand function given to us, the derivative of negative 8p is negative 8. The derivative of 104 is 0. So in parentheses up on the top, you have negative 8. That's the derivative of the demand function. And then we divide that by the original demand function, and that becomes our denominator. So when we clean this up, we see negative p times negative 8 is really a positive 8p. And then we have the denominator, which is the original demand function. So this is what we call the elasticity function. And notice that it depends, on the right, entirely on the price. So if you give me a particular price, like $7, I can quickly find the elasticity value. We call this the general elasticity equation, or the general elasticity function, for the given demand equation. Once we have the general elasticity function, then we can substitute any price p into that elasticity function, and that will give us the elasticity value. So in this particular example, we're looking at a price of $7, and so we want to look at the elasticity value at 7, or E of 7. So we plug 7 into the elasticity function that we just found. On the top we have 8 times 7. Down below we have 7 plugged into the original demand function. So that gives us 56 divided by 48 when we do some arithmetic, or a final elasticity value of 1.167. So we now need to interpret what this means. So in this situation, our E value, our elasticity value, is greater than 1. So this is an elastic price point. That tells me that my quantity in demand is decreasing more quickly than my price increase. That results in decreasing revenue, and so our interpretation here for this particular elasticity approach is to say the following. If we take a price point of $7 and we increase that by exactly 1%, then that is going to lead to a corresponding 1.167 decrease in demand. So the 1.167 that you see right here is already a percentage. It's already been converted. And so this particular approach is kind of handy because it's always a small 1% increase in price, and then the elasticity value is the corresponding percent decrease in demand. So you can see we're only increasing the price here by 1%, but our quantity in demand is going down by a little more than 1%, so therefore we should expect our revenue to decrease in that situation. Another way to think about this, if our current price is $7, we can't increase the price by 1%, because if we do, revenue will decrease. Let's do one last example here, but we're going to do this in depth. We'll go ahead and do another example of an elasticity calculation with the demand function given to us. But once we're done with that, we're going to explore this a little bit further and try to tie it back to things that we've seen in this course in previous topics. So our demand function here is given to us as d of p is equal to negative 3p plus 300. We're going to look for the elasticity value at a price point of $20. So our elasticity function is going to look like this. We have negative p multiplied by the derivative of demand. So keep in mind that we're getting the derivative of negative 3 directly from the demand function up at the top. And so we're getting that from the derivative of negative 3p is negative 3. And then of course in the denominator, the bottom, we have the original demand function, which we can just copy directly from what's given to us. So our elasticity function can be simplified up on the top to be positive 3p, and then we have the demand function down on the bottom. So that's our general elasticity function. That tells us the elasticity value for any price point, including the price point at 20. So E of 20 is equal to, up on top, 3 times 20, divided by, in the denominator, we have negative 3 times 20 plus 300. So a little bit of arithmetic gives us 60 up on top, 240 down below, or 0.25. So when we look at this, we have an elasticity value that is less than 1. So this is elastic. We know then that revenue is increasing here, and our interpretation is pretty straightforward. For the elasticity equation that we've been using here, a 1% increase, that's always the case, we assume a 1% increase in the price, and then the elasticity value is the corresponding percent decrease in the demand. So a 1% increase in the price here leads to only 1/4 of a percentage of a decrease in the demand. So we can increase the price here by a little bit, because the decrease in demand is only 1/4 of that, and therefore this particular price increase will lead to our overall revenue to increase or to get larger. So now let's think about how this relates to what we already know about revenue functions and demand functions and things like that. We can ask this question: what is the revenue itself doing at $20? In the previous calculation, we know that if we increase the price by a small percentage from $20 by 1% to $20.20, we know the revenue is going up. But we don't know how much the revenue actually is at that particular price point, nor do we know how fast that revenue is actually growing. So in order to calculate those kinds of things, we have to go back to the original revenue function itself. So for example, if I know that the demand function is given as negative 3p plus 300, then I can compute what the revenue function should be. So I have R of P is equal to the price P times the quantity Q. In this case, the quantity Q is given by the demand function. So Q is equal to negative 3 plus 300. So our revenue function can be found. It's a quadratic as we've seen before, but now the revenue function is given in terms of P and not Q. And it's negative 3p squared plus 300p. So at a price point of $20 per item, we can do the arithmetic, the calculation, that then tells me that my total revenue at that particular price point should be $4,800. So that's how much actual revenue we're earning at that particular point. And if we wanted to know what would happen if we were to measure the rate of change, then we would simply find the derivative of the revenue function, or the marginal revenue function, and then compute with that. So in this case, the marginal revenue function is the derivative of R of P, and so the derivative of negative 3p squared on the revenue function is negative 6p, and the derivative of 300p is 300. So this is my marginal revenue function, negative 6p plus 300. And so I can measure the rate of change of revenue at any point simply by plugging in a price into this equation. So if I plug in 20, R primed at 20 will be negative 120 plus 300, which is 180. Now remember, this is a rate of change, and so the units are important that we pay attention to those. This of course is dollars of revenue, but keep in mind that the independent variable here is P. So we have to pay attention to the interpretation, which would be as follows. If we were to increase the independent variable price by 1 unit, $1, that's our marginal change, from $20 to $21, then that will result in about $180 of additional revenue. So here's a picture of what this looks like on a graph. We have here a revenue function where on the horizontal axis you have P price is our independent variable, and on the vertical axis we have total revenue. So what we're doing here is we're picking a point. Let's say the price is $20, and you can see that if you go over to the vertical axis, we're just under $5,000 of revenue, and of course we just found at $20 our total revenue was $4,800. So that matches. And then if you were to draw a tangent line at that particular point, this is going to give you a measurement of the rate of change. We just calculated the marginal revenue at 20. We found that it was 180. And so at that particular price point of $20, what we see then is that if we were to increase the price by $1, then we would see $180 in additional revenue. So we can build on this example and ask, when is the elasticity value unitary? Remember, unitary elasticity means that our E of P function is equal to 1. Now recall, for this particular example, our elasticity function is 3p divided by negative 3p plus 300. So this is the elasticity function that we want equal to 1. So we need to solve this equation for P. What price gives us unitary elasticity? Well, the easiest way to do this, since we have a fraction on the left, is to remove the fraction. And so we do this by multiplying both sides of the equation, including the right, by the quantity negative 3p plus 300. When we do that, we end up with 3p on the left, all by itself, and on the right, negative 3p plus 300. And we can solve this equation pretty easily by adding 3p to both sides of the equation. That gives us 6p on the left and 300 on the right, and then of course we just divide both sides by 6 to get a price of 50. Now, this tells me then that at a price of $50, we have unitary elasticity. So the question then is, well, so what? What does that mean? So let's take a look at that. Once again, here's the picture of that revenue function. We have price on the horizontal axis and revenue on the vertical. And remember that we just found that P equals 50, a price of $50, gives us an elasticity value of exactly equal to 1. So if we look at what's going on at a price of 50 on the revenue graph, we see here that that's the exact maximum point of the revenue function. And so at that particular point, our derivative is exactly equal to 0, and therefore our revenue is maximized. So we notice here then that the derivative of the revenue function will be equal to 0 at exactly the same point where the elasticity value is equal to 1. So this is just another way to maximize revenue. We now have two. We can maximize revenue by setting the marginal revenue function equal to 0, which we see visually on this picture as the slope of the tangent line is equal to 0, or we can find where elasticity is unitary. So here's an interesting graph that tries to show several things at once. Notice you have the elasticity curve here, E of P. So what I've done here is I've graphed that function. E of P is equal to 3P divided by the demand function. So this is what the elasticity curve looks like. I also have the flat line that goes through the number 1. So this is the unitary line, you might say. And that happens, as we just saw, at a price point P equals 50. That was where revenue was maximized. So notice to the left of 50, to the left of that vertical line that you see there, all of the values on the elasticity curve are below 1. They're all below that flat blue line that goes through 1. So those are all inelastic price points. On the other hand, all of the values or all of the prices to the right of that vertical line through 50, all of those elasticity values on the E curve are above 1. They're above that flat line that goes through 1. So if they're all values that are greater than 1, then those are what we call the elastic price points. So to the left of the vertical line at 50, all of your revenue points. So to the left of that vertical line that goes through 50, those are all prices where a small price increase should lead to increasing revenue. And then on the right side, those are all the price points that correspond to places where small price increases should lead to decreased revenue. Now notice all of these curves, there's a vertical line, a horizontal line, and then the elasticity curve. All of those curves intersect at that point right there when P is equal to 50, but notice it's also when your elasticity value is unitary. So unitary elasticity, E, which is measured on the vertical axis, is equal to 1 when the price is equal to 50. Of course, we just saw that on the previous slide. But if you were to take that particular point and then go up and then zoom out so that you could see the revenue curve, then what's going to happen is that's the point where your revenue should be maximized. And sure enough, we've seen that already. So in this example, we've been exploring how we can maximize revenue by finding when the elasticity value is unitary. But in topic 5, we also saw that we could maximize any function, including revenue, by finding the derivative of that function and setting it equal to 0. So let's go ahead and explore what would happen if we used the approach from topic 5 just to make sure that it matches what we're getting with this unitary elasticity approach. So remember that we have d of p is equal to negative 3p plus 300. Keep in mind, the left side of that equation, d of p, is really q, quantity. So it's quantity equals negative 3p plus 300, because that's the demand function. And the demand function always relates quantity and price. So let's go back and build our revenue function. Revenue as a function of p, because we're letting p be our independent variable here in this topic, is equal to price times quantity. But price times quantity is the same thing as price times d of p, or price times demand. And we're given the demand function here, and so our revenue function is p times the quantity negative 3p plus 300. And then when we distribute the p on the outside, our revenue function becomes negative 3p squared plus 300p. So this is the revenue function that depends on the price p, not the quantity q. Once you have the revenue function, it's easy to take the marginal revenue function. The derivative of negative 3p squared is negative 6p, and the derivative of 300p is 300. And from topic 5, we know we set that equal to 0, which you see here. And when we solve that by adding 6p to both sides, let's say, and then dividing by 6, we end up with a price of 50, which of course is exactly what we've already discovered. So it all fits together really nicely. As we've been saying, you can maximize revenue either by setting the derivative equal to 0 for the revenue function, as you see here on this slide, or building the elasticity function and then finding out when that has a value of 1, when it's unitary. So this concludes the lecture material for topic 6. You're now ready to work on the lecture project, the online homework, and the topic quiz. So please don't delay too much on that. And if you have questions, please post them to the forums. Thanks and good luck.